Section 5.2 is on polynomials, linear factors, and zeros. If p of x is a polynomial function, the zeros of the function are the x's when p of x is equal to 0. In other words, what are the values of x when y is equal to 0? To find the zeros of a polynomial function, you need to solve the equation. As we saw with quadratic functions, one way to do this is by factoring. So let's take a look at our first example here. It says, what is the factored form of x cubed plus x squared minus 12x? So the first thing I'm noticing is I have a greatest common factor of x that I could take out. So that's going to leave me with x squared plus x minus 12. And then the trinomial in the parentheses will factor into x plus 4, x minus 3. So that's the factored form. Roots, zeros, and x-intercepts of a polynomial function are all related. And here's a chart from your textbook. Okay. The following equivalent statements about a real number b and the polynomial p of x, don't get scared off by that, is as follows. X minus b is a linear factor, because the graph of that would be a line, of the polynomial p of x. B is a zero of the polynomial function y equals p of x. B is a root or a solution of the polynomial equation p of x equals 0. And b is an x-intercept of the graph of y equals p of x. In other words, b can be called a zero if it's a function, a root or a solution if you're looking at the equation, or a x-intercept if you're looking at the graph. So let's take a look at another example here. This says, find the zeros of y equals, and fortunately we already have it in factored form here, the quantity x minus 3 times the quantity x plus 4 times the quantity x minus 1, and then graph the functions. So in other words, what are the x's when y is equal to 0? So if this whole thing were to be equal to 0, so that would mean that x minus 3 would equal 0, x plus 4 would equal 0, and x minus 1 would equal 0. So my zeros are going to be x equals 3, x equals negative 4, and x, whoops, that should be a 0, x equals 1. So what's the graph of that going to look like? Well, those are my x-intercepts, so that's where the graph is going to cross the x-axis at those points. Okay, now because I know that my leading coefficient is going to be 1, because if I multiplied my x's I'd get an x cubed. I don't have a coefficient in front of my x's. So my a is equal to 1 and my n is equal to 3. So this is a positive number and this is an odd number. So from the last section I know that my end behavior is going to be down and up, so down on the left and up on the right. So my graph could look something like this. Don't know exactly how high and how low it's going to go, but that's what the graph would look like. The factor theorem describes the relationship between the zeros and the linear factors of a polynomial function. The expression x minus a is a factor of a polynomial if and only if the value a is a zero of the related polynomial function. In other words, now we're going to be doing these problems backwards. So here's an example. We need to write a polynomial function in standard form that has zeros of 1, negative 1, and 4. So in other words, x is equal to 1, x is equal to negative 1, and x is equal to 4, and I need to turn that into a polynomial function. Well, to do that, I'm going to set each one of these equal to 0. So this means x minus 1 equals 0, x plus 1 equals 0, and x minus 4 equals 0. So now my polynomial function is going to be the product of each of those linear terms. So I have to multiply that. Actually, what I'm noticing is that this is going to turn into a difference of squares. So I have that times x minus 4. So I just FOIL that, and that's going to give me x cubed minus 4x squared minus x plus 4. So my polynomial function is going to be y equals, or you could use f of x or p of x, equals x cubed minus 4x squared minus x plus 4. If a polynomial has a repeated factor, the repeated factor creates a multiple 0. So for example, in the polynomial f of x equals the quantity x minus 1 squared, remember that means x minus 1 and an x minus 1, times the quantity x plus 3 times the quantity x minus 4. This x minus 1 is a repeated factor and has multiple zeros at x equals 1. Since this factor appears twice, we say that 1 is a 0 of multiplicity 2. In other words, it's going to hit the x-axis right there, and we say that there's actually 2 zeros at that point. So how do these multiple zeros affect a graph? If a is a 0 of multiplicity n in the polynomial function y equals p of x, then the behavior of the graph at the x-intercept a will be close to linear if n equals 1, close to quadratic if n equals 2, close to cubic if n equals 3, and so on. So let's take a look at what this is going to look like. So this example says find all of the zeros of the function f of x equals x cubed minus 4x squared plus 4x and state the multiplicity of the zeros. So the first thing I would like to do is factor that, x cubed minus 4x squared plus 4x. Taking out a greatest common factor, I get x squared minus 4x plus 4. And I recognize that trinomial in the parentheses as being a perfect square trinomial, which factors into x minus 2 squared. So if I need to find my zeros, I'm going to make that equal to 0. So that means that I will have a 0 at x equals 0, and I will have a 0 at x equals 2, and that's going to have, because that is squared, that's going to have a multiplicity of 2. If the graph of a polynomial function has several turning points, it can have a relative maximum and a relative minimum. A relative maximum is the y value at an up to down turning point, like the top of the mountain, and a relative minimum is the y value at a down to up turning point at the bottom of the valley. Oops, hold on, bring that down here. So here's a picture. So for this graph, at this point right here, we would have a relative minimum, because that's not the total minimum point of the graph, because it does head towards negative infinity, but a relative minimum, and then this point right here would be a relative maximum, not the overall maximum, because here it tends towards positive infinity. So our last example here says find the relative maximum and relative minimum of the graph of f of x equals x cubed minus 9x and round to the nearest tenth. So to do this, I'm going to graph it on my calculator. Okay, so here I've put into y1 x cubed minus 9x, and I'll go ahead and graph that. And here I have the graph of the function, and I could change my window a little bit because I'm going to have a relative maximum up here and a relative minimum down here. I don't actually have to do that. I think I can still do it without seeing the whole thing. So I'm going to do second trace, and I'm going to go for my maximum first. So let's go down to 4 and hit enter. And this is going to do my left bound and right bound thing again. So I have to move my cursor over to the left of my maximum. Okay, that's good there. Hit enter. And now I need to move it over to the right. It's a little off the screen, but he'll be coming back. There he is. And I'll hit enter, and that's my right boundary. And if I hit enter again, it will tell me that the coordinates of that point is approximately negative 1.7, comma 10.4. So remember, your relative max or min is going to be the y value. So I'm going to have a relative maximum value at y is approximately equal to 10.4. So I will have a relative max at y is approximately equal to 10.4. And let's look at our graph again, and I would have a relative min down here, and I'm not going to take the time to calculate, but that's going to be, I did that earlier, that's going to be a relative minimum at y is approximately equal to negative 10.4. So in this section, we took a look at polynomials, their linear factors, and their zeros, how to find the zeros, what that means, roots, zeros, and y-intercepts, and then how to find the maximum, relative maximum, and relative minimum of a function.